Hello guys, my name is Craig and welcome to Peri Solutions. In today's video, we shall be looking at Laplace Transforms. But before we start, please make sure that if you're new to my channel, you hit the subscribe button and turn on the notification bell so that you don't miss out on any new videos. So under Laplace Transforms, we want to look at the introduction, right, to the topic. Then we shall look at the definition of a Laplace transform. Then we'd like to look at the properties of Laplace transforms, and under the section, we'd like to look at the Laplace transforms of some standard functions. And those are the ones that we're going to use to attempt this exercise together, right? So the Laplace transform method is a method that is used to solve differential equations with initial and boundary conditions. And the beauty of using this method is that you can solve differential equations, right, with initial conditions directly and without necessarily having to first of all find the general solution, then evaluating the arbitrary conditions using the initial conditions. So that's the beauty of using the Laplace transform method, right? So for the definition of a Laplace transform, let's say we've got a function f of t. So if f of t, right, if we say let f of t be a function such that, right, f of t. So let's say f of t is a function that is defined for all values of t that are greater or equal to 0, right? The Laplace transform of f of t, which is denoted by L f of t, right, would be equal to, this will be equal to the integral of e to the power minus st f of t dt. And this will be from 0 to infinity, right? So this is what we call the definition of a Laplace transform. So we're saying if f of t is a function such that it is defined for all values of t that are greater or equal to 0, the Laplace transform of f of t would be equal to the integral of e to the power minus st f of t dt from 0 to infinity, right? So if this, the integral on the right hand side, if it exists, this will be a function of s, and usually it is written as f of s, right? So I'm sure from this you can see that s is a parameter such that f of s would be equal to the Laplace transform of f of t, which is equal to the integral of e to the power minus st f of t by dt from 0 to infinity, like this. So this is the definition of a Laplace transform. And of course here s would be either a real number or a complex number, right? So now we'd like to look at the properties of Laplace transforms. So now let's say we've got two functions, right? And let's say let f of t and g of t be functions such that these are defined for all positive values of t. And let's say we've got constant k, right? Constant k like this. Okay, so the first property that I would like to get is the one whereby if we say the Laplace transform of k f of t is just the same as k multiplied by the Laplace transform of f of t, like this. So this is the first property that I would like to look at. And the second one states that the Laplace transform of f of t plus g of t is equal to the Laplace transform of f of t, right, plus the Laplace transform of g of t, like this. So these are the two properties that we have, right? So let me do this. let me write down this definition here such that it is easier for us to just refer back. So we said Laplace transform of f of t is equal to the integral of e to the power minus st f of t by dt from 0 to infinite, like this, and this. We also said that can be f of x, capital letter f of x. So now I would like to prove these two theorems, right? And remember we said this is for all positive values of t, right? So for the first one, if we would like to prove the first theorem, for the first theorem, right? For proving these, we shall prove these from the definition that the Laplace transform of f of t is simply equal to that. So for one, we've got let me use this one. For one, we've got the Laplace transform of k f of t, right? So from the definition, this would be equal to the integral from 0 to infinite of e to the power minus st multiplied by k f of t, right, by dt. But you know that when integrating, we can take out the constant here. So if we take out the k, right, we have that st f of t by dt. And we know that the integral of e to the power minus st f of t by dt from 0 to infinite, this is what we are calling the Laplace transform of f of t. So this will just be the same as k multiplied by the Laplace transform of f of t. So this proves the first property that we have here. And now proving the second one. For the second one, we've got the Laplace transform of f of t plus g of t, like this, right? So proving this from the definition, we're saying that this is equal to the integral from 0 to infinite of e to the power minus st, right, multiplied by f of t plus g of t by dt, like that. Then we know that we can split, since this is a summation, we can actually split here. Then we have the integral from 0 to infinite of e to the power minus st of f of t by dt. Then we say plus, right, the integral from 0 to infinite of e to the power minus st of g of t by dt. And this will be equal to, so we know that the integral of e to the power minus st f of t by dt from 0 to infinite, this is simply the Laplace transform of f of t, right? Then plus the integral of e to the power minus st g of t by dt from 0 to infinite. This is simply the Laplace transform of g of t. So Laplace of g of t. So now this proves the second theorem here, right, that we have. So if we would write it down, we're saying we also have Laplace transform of k f of t being equal to k Laplace transform of f of t, like that. So that's 1, 2. We also have Laplace transform of f of t plus g of t being equal to the Laplace transform of f of t plus the Laplace transform of g of t, like that. So this is the first situation that we have. So now I'll allow you to erase this. so that we can go on to look at Laplace transform. We can go on to look at the Laplace transforms of some standard functions. Okay, so now we shall release this. Okay, so now we shall look at the Laplace transforms of some standard functions. So firstly, we'd like to look at the Laplace transform of a constant, right? So Laplace transform of a constant, Laplace transform of a constant. Right. So for a constant, we shall say let f of t be equal to constant a, such that the Laplace transform of a from the definition will simply be equal to the integral from 0 to infinite of e to the power minus st. But now in place of f of t, we are now putting a. So multiplied by a, and this is with respect to t. So of course, a being a constant, you can take it out, such that we've got a integral of e to the power minus st with respect to t from 0 to infinite. And this will be a multiplied by, so if we integrate this with respect to t, we know that we're dropping this in the denominator, such that we've got minus e minus st over s, and this is from 0 to infinite, like this. Then, if we substitute the limits, e to the power minus infinite, this will simply give us 0. So we've got the 0, the minus, right? Now, if we substitute 0, e to the power of 0, we know is 1. So this will be minus 1 over s. Right, but as we can see here, we've got a minus and a minus, which will give us a plus. So that will be a multiplied by 1 over s, which is simply a over s. So basically, the Laplace transform of a constant is simply equal to a over s. So if we have a as 1, that will simply be 1 over s. Right, if we've got a as 5, the Laplace transform of 5, that will simply be 5 over s. So we can put this down as a general result that the Laplace transform of the constant a is simply equal to a over s. Right, this is 1. Then now, 2 would like to look at the Laplace transform of e to the power of at. Right, so let me just write Laplace transform Lt of e to the power of at, like that. So from the definition, right, in place of f of t, we now have e to the power of at. So the Laplace transform of e to the power of at will now be equal to the integral from 0 to infinite of e to the power minus st multiplied by. So now in place of f of t, right here where we put f of t, we're now putting e to the power of at. So this is now e to the power of at, and this is with respect to t. Such that now if we evaluate this using the laws of indices, we now have the integral from 0 to infinite. So basically when we evaluate this, these two, we have to maintain that negatively. So this will be e to the power minus s minus a, like this. Such that that will simply be minus a, minus s plus a, minus s plus a. This is one and the same. So this is now with respect to t. So now if we carry out this integral here, we now have, so we know this is with respect to t, so there's a t there, right? So if we integrate this with respect to t, we're dropping that, right? And you know there's a negative already here. So that's simply minus e to the power minus s minus a to the power of t, times t over s minus a, like this. Okay, and this is from 0 to infinity, like this. So now if we substitute the limits that we have, right, e to the power of infinite, or maybe e to the power minus infinite, that would just give us a 0, then minus, open bracket, now we substitute the lower limit. So if we say e to the power of 0, we get a 1. So this is now minus 1 over s minus a. And minus, the sign will simply change to a plus, such that you have 1 over s minus a. Right? So basically the Laplace transform of e to the power of at is 1 over s minus a. And this is only valid if a is greater than 0 but less than s. Right? So we can say for a is a is greater than 0 but less than s. And if we would like to say, let's say we want to find the Laplace transform of e to the power minus at, right? So now the only difference is that in place of a, we're now substituting a minus a. So this will be 1 over s minus, then a, we're putting a minus a, and this will be 1 over s plus a. So these are the two quotable results that we can have, right? And this is always also valid under those conditions. So we are also saying that 2, the Laplace transform of e to the power of at is equal to 1 over, and this is valid for s is greater than 0, right? The first one here. So this, we said that would be s minus a for s is greater than 0 and greater than a, right? So s is to be greater than 0 and it is to be greater than a. And we also say the Laplace transform of e to the power minus at would be equal to 1 over s plus a. So this is valid for s is greater than 0, right? So the two quotable results. So now I would like to look at the Laplace transform of hyperbolic function or sine, of course. So allow me to erase this section, right, for finding the Laplace transform or deriving the Laplace transform of the constant. Right. Okay. All right. So now we say we would like to look at how we find the Laplace transform of, let's start off with the sine hyperbolic function of at, right? Then we can move on to look at the cosine hyperbolic function of at. So we know that basically sine hyperbolic function of at is equal to 1 over 2 multiplied by e to the power of at minus e to the power minus at. Right. So finding the Laplace transform of sine hyperbolic function of at is just the same as finding the Laplace transform of that. And from this theorem here, we can take out the half such that we're simply saying half multiplied by the Laplace transform of e to the power of at minus the Laplace transform of e to the power minus at, right, like this, right? Then, now we can find these. So we're saying half multiplied by Laplace transform of e to the power of at, you see that's 1 over s minus a, then minus the Laplace transform of e to the power of minus at, you see that's 1 over s plus a. Right, so if we combine these two, right, here we know that the common denominator is simply the product of these two, right, which is supposed to be a difference of two squares. Since if we multiply these two, there will be a difference of two squares. So that's simply a squared minus a squared. Then this is over. So this into that we get s plus a, then minus s plus a into a squared minus a squared, we get s minus a. And now, because of this negative, we'll put it in brackets like that, and that will evaluate to s plus a minus s plus a over a squared minus a squared, like that. Then s minus s gives us 0, a plus a gives us 2a, then 2a multiplied by this 2, so 2 into that 2a, that will give us an a. So this will simply be a over a squared minus a squared. Right. So this is the general result that we get if we define the Laplace transform of the sine hyperbolic function of at. So we can actually write it down here. Right, that the Laplace transform of sine h of at is equal to s over, sorry, it's supposed to be a over s squared minus a squared for s greater than 0 as well. Right. So now let's move on to look at the Laplace transform of cos at, or the cos hyperbolic function of at. So allow me to erase this part in black here. Okay, so now looking at the Laplace transform of cos at, or the cos hyperbolic function of at, right? What's simply changing is that for cos at, this side is a plus. So cos hyperbolic of at is half, right, e to the power of at plus e to the power of minus at. Right, so everything else is the same here, but what's simply changing is the sine base, right? So let's start off from here. Right. So let's say the Laplace of cos at is equal to, so we say everything else is the same, but what's changing is simply the sign. The sign is changing to plus. So we're saying half of 1 over s minus a plus 1 over s plus a, like that. Then, for simplifying this, we have half of, denominator is still the same, s squared minus a squared is over, so now s minus a into a squared minus a squared, we get s plus a. So s plus a, then plus s plus a into a squared minus a squared, we get s minus a. So you've got a minus a, that gives us 0. Then s plus s, that gives us 2s. Then because of this half, we say 2 into that 2, we get 1. So then we end up having s in the numerator, then a squared minus a squared in the denominator. So this is also a quotable result for cos hyperbolic function of at. So we say the Laplace transform of this will give us s over a squared minus a squared. Right. So let me write it here. So allow me to erase that. Okay, so we're saying that this is 5, or 5 is in the Laplace of cos AT is equal to s over s squared minus a squared. And this is valid for s is greater than 0. Also has to be greater than a, right? And now we'd like to look at how we derive the Laplace transforms of cos AT and sin AT. But to do that, we shall do this from Euler's formula, which states that e to the power of iat is equal to cos AT plus I sin AT. Right. So now if we evaluate the Laplace transform from both sides, right, the left hand side and the right hand side, we say that the Laplace of e to the power of iat should be equal to the Laplace of cos AT plus I Laplace of sin AT, like this. Then we know we can find the Laplace transform of this, and this will simply be 1 over s minus a, but in this case our a is ia, so ia. Right, so first of all, let's just evaluate what's on the left hand side. So if we rationalize this, that will be s plus ia over a squared plus a squared. Right, and if we split this, this will simply be s over s squared plus a squared, then plus a over a squared plus a squared, s over s squared plus a over s squared plus a squared, like that. Okay, so now this is the evaluation of what's on this left hand side. So now if we are to compare the real parts and the imaginary parts, we're saying s over s squared plus a squared, then plus a over a squared plus a squared is equal to the Laplace transform of cos AT plus I Laplace of sin AT, such that now comparing the row parts, we see that the Laplace transform of cos AT is equal to is equal to s over a squared plus a squared. So we say that the Laplace of cos AT is simply equal to s over a squared plus a squared. Then the Laplace transform of sin AT is simply equal to this, right? This is now the imaginary part. That will be a over a squared plus a squared. And both of these are valid only when s is greater than 0, right? So we will actually add them here. Okay, so let's see if we can add them. So allow me to just erase the top part so that I can create some space. Right, so we're saying that this is now what? This is 6. For 6, you say the Laplace of cos AT is equal to s over a squared plus a squared for s greater than 0. Then 7 Laplace of sin AT is equal to, this is now a over a squared plus a squared for s is greater than 0. Then the last one that I would like to get, for this one, I'm just going to give you the general result that we need to know. Okay, so let me erase this. Okay, and this as well. Okay, so now the last one, this is the eighth one. It will be the Laplace transform of t to the power of n. So the Laplace transform of t to the power of n, we say that n factorial over s to the power of n plus 1, right? And this is only when n, this is valid when n is a non-negative integer, and s has to be greater than 0. So please take note, for n is a non-negative integer. Right? So now I'd like to use those results that we derived to attempt those questions right here. Okay, so for the first one, so it said that find the Laplace transforms of the following functions. Okay, so the first one is that we want to find the Laplace of 2t squared plus 3, and we know that we can split this such that we say 2 Laplace of t squared plus the Laplace of 3, right? And then this will be 2 multiplied by, right, t squared, in this case our n is 2, right? So 2 factorial, this is 2 over s to the power of 2 plus 1, that will be 3. Then plus Laplace transform of 3, we say that will be a over s. In this case our a is 3, so that's just 3 over s. So that will be 4 over s squared, sorry, this is s cubed plus 3 over s. So now if you have to evaluate that in the single fraction, common denominator s to the power of 3, that will be 4 plus 3s squared. So this is the result that we get for the first question. Then for number 2, we want to evaluate the Laplace transform of 4t squared minus 5t plus 6. And we know we can split this, right, to have 4 Laplace of t squared, right, minus 5 Laplace of t, then plus the Laplace of 6. And this will be 4 multiplied by t squared, Laplace transform of t squared. This is simply n factorial 2 factorial over s to the power of n plus 1, which is s to the power of 3, then minus 5 multiplied by the Laplace transform of t. This is t to the power of 1. So this is 1 factorial over s to the power of 1 plus 1, that will be 2. Then plus Laplace transform of 6, that will simply be 6 over s. So this will give us 8 over s to the power of 3 minus 5 over s squared plus 6 over s. So now if we evaluate this as a single fraction, common denominator there will be s to the power of 3, right? Then we've got 8 minus 5s plus 6s squared. So this will be the final result that we get for the second question. Then now moving on to the third question. For the third question, we're going to find the Laplace transform of 1 plus e to the power of t squared, which we know we can expand first. So we can expand this 1 squared, this is 1, then 1 times e to the power of t, 1 times e to the power of t, right, times 2, that will simply be plus 2e to the power of t, then e to the power of t squared, that's plus e to the power of 2t. So now find the Laplace transform of that. Laplace transform of 1 is simply 1 over s, plus 2 times the Laplace transform of e to the power of t. In this case our a is 1, so that will be simply 1 over s minus 1. Then plus the Laplace transform of e to the power of 2t. In this case our a is 2, so that will simply be 1 over s minus 2. And we can evaluate this as a single fraction. Common denominator being s minus 1, s minus 2. Right. then s divided into that, we get this and this, which when we multiply, that will give us, or maybe before we multiply, let's just write it down, then plus this into that, we get s times s minus 2, multiply by 2, so that's 2s times s minus 2, then plus s minus 2 into that, we get s times s plus 1, so s times s plus 1 times that 1, right? So of course, we know we need to evaluate what's in the numerator a, and that will evaluate to s squared minus 3s plus 2, right, plus 2s squared minus 4s plus s squared minus s, right, over that. So now I'm just evaluating what's in the numerator. So what's in the numerator will give us s plus 2s plus s, that will give us 4s squared. So s squared plus 2s squared plus s squared, that will give us 3, 4. So 4s squared, then minus 3s minus 4s minus s, that will give us minus 8s. Then 2 plus, is this an s? Alright. And then this is just a 2. So we've got one constant here. Okay. So that's just a plus 3 over s times s minus 1, s minus 2. So this, all of this is over s times s minus 1, s minus 2. So if we factor out the 2 in the numerator b, right, that will be 2 times 2s squared minus 4s plus 1 over s minus 1, s minus 2. So that will be the final result that we get for the simplification of number 3. So now I'd like to move on to look at number 4. And to do that, allow me to erase this. Okay, so now we shall look at number 4. For number 4, we are required to simplify the Laplace transform of cos squared at. Right, this is now number 4. So we want to find the Laplace of cos squared at. And to do that, we shall need to use the identity whereby we say that cos 2at is equal to 2 cos squared at minus a, such that cos squared at would be equal to half of cos 2at, right? Oh, in this case we don't have to say 2. Why? Because we can leave the 2 there, it's necessary. So half cos 2at, right? Then that will be what? Plus 1, like this. So in other words, the Laplace transform of cos squared at would be half Laplace transform of cos 2at, right, plus the Laplace of 1. Then we can put that in brackets. Okay. Then for further simplification, we can now say that, so allow me to use this part here. So we can now say that Laplace half multiplied by, so Laplace transform of 2at, cos 2at would be s over a squared plus, in this case our a from here 2a squared, that will give us 4a squared. Then plus Laplace transform of 1, that's simply 1 for s. So if we have to combine that, we've got a squared plus 4a squared over, that's into that, we get s times s, that's a squared plus ss, that will give us a squared plus 4a squared. Right, then that will give us half of 2a squared plus 4a squared over s, right, a squared plus 4a squared. And that will simplify to, so if you say 2 into 2a squared, that will give us a squared. Then 2 into 4a squared, that will give us a plus 2a squared over s multiplied by a squared plus 4a squared. So that's the result that we get for number 4. And now we shall move on to look at number 5. Right? But for number 5, we need to derive an identity for sine cubed at. Right? So allow me to erase this so that I do the derivation here. Okay. So now, right. So we can say sine 3at is equal to sine 2at plus 80. Right, then here we can apply an identity that's sine 2at cos 80 plus cos sine 80 cos 2at. Exactly. Then we now say cos 80 sine 2t is 2 sine 80 cos 80. Then plus sine 80. So in this case, we need sine cube. So we shall eliminate anything that will give us a cos. So we put 1 minus 2 sine squared 80. Like that. Then this will simplify to 2 sine 80 cos squared 80 plus sine 80 minus 2 sine cubed 80. Then in place of cos squared 80, we can put 2 sine 80, then 1 minus sine squared 80. Right, then plus sine 80 minus 2 sine cubed 80. Then that will give us 2 sine 80 minus 2 sine cubed 80 plus sine 80 minus 2 sine cubed 80. Then if we group like terms, we've got 2 sine 80 plus sine 80, that will give us a 3 sine 80 and minus 2, that's minus 4 sine cubed 80, such that this is sine 380. So if we make sine cubed 80 subject to the formula, we're taking this aside and this aside. So sine cubed 80 would be 1 over 4 of 3 sine 80 minus sine 380. Like this. So this is the identity that we need, such that we're saying that the Laplace of sine cubed 80 is equal to the Laplace transform of 1 over 4 of 3 sine 80, right, minus sine 380. Right, like that. Then here we know we can take out the constant 4, then say Laplace of, or rather let me say 3 Laplace of sine 80, right, minus Laplace of sine 3at. So that will be 1 over 4, 3 times sine 80, we know that's a over a squared plus a squared. So this is now 3a over a squared plus a squared minus Laplace transform of sine 3a. Right, this is also 3a over a squared plus a, in this case our a is 3a, so 3a squared that gives us 9a squared. So if we make that one fraction, we've got a squared plus a squared, this is in the denominator, a squared plus 9a squared. This is over. If we say this into that, we've got 3a multiplying a squared plus 9a squared minus 3a multiplying a squared plus a squared. Like this. So if we further simplify, we've got 3a squared minus 3a squared to give us a 0. Then 3a times 9a squared, that will give us a 27a squared. Then minus 3a, so 3a times 9a squared, that will give us 27a cubed minus 3a times a squared, that will be 3a cubed. So if we carry out the subtraction here, we get what? 24a cubed. So this is 24a cubed divided by 4 here, that will simplify to a 6a cubed. So rather, now just write 6a cubed over a squared plus a squared times a squared plus 9a squared. Like this. So that's how we calculate the Laplace transform of sine cubed at. Right, now we shall move on to problem number 6, which requires us to find the Laplace transform of cos 5t cos 2t. So allow me to erase this. Right. Now, finding the Laplace transform of cos 5t cos 2t, we need to use the identity that, let me write it here. We know that cos alpha cos beta is equal to half of cos alpha minus beta plus cos alpha plus beta. So this is the identity that we have to use, such that cos 5t cos 2t would be equal to half of cos, right, 5t minus 2t, that's 2t, plus cos 5t plus 2t, that's 7t. So we're simplifying the Laplace transform of this. So we can say the Laplace of cos 5t cos 2t is equal to 1 over 2 Laplace of cos 3t plus Laplace of cos 7t, like this. Then this will be half of Laplace of cos 3t. We know that this is s over a squared plus, in this case our a is 3 squared, that will give us a 9, plus s over a squared plus, in this case our a is 7 squared is 49. So simplifying that, that will be half of s squared plus 9 times a squared plus 49. So s squared plus 9 into this, we get s times s squared plus 49. So s times s squared plus s to the power 3 plus s times 49 plus 49s. Then plus s squared plus 49 into this, we get s squared plus 9 then times s, that will be s to the power of 3 plus 9s. Like this. Then if you further simplify, that will give us half sine s cubed plus s cubed plus 2s cubed, then 49 plus 49s plus 9s plus 58s. And this is over that. So s squared plus 9, s squared plus 49. Like this. Then here we know we can factor out the 2, such that we get s to the power of 3 plus that 29, yeah, 29s, which you can choose to write as s, then s squared plus 29. So s squared plus 29 over s squared plus 9 times s squared plus 49. So that's how we simplify cos 5t, the Laplace transform of cos 5t cos 2t. Then now if we simplify the Laplace of cos 8t sine 2t, we do the same thing, but now we apply an identity, right? And the identity that we apply the identity that, let me write it down for you. So sine alpha cos beta is equal to half multiplied by, this will be what? This will be sine alpha minus beta plus sine alpha plus beta. But now you really have to be careful, because in this case your alpha is 2t, then your beta is 8t. So sine 2t cos 8t would be equal to half of sine 2t minus 8t, that's minus 6t, plus sine of beta, alpha plus beta, 2t plus 8t, that's 10t. So now after you've done this, you simply apply the same thing that we did here. You find the Laplace of this, the Laplace of that, then you combine that to give you a single fraction, then you just simplify everything. So this was looking at the Laplace transforms, and we got to look at the introduction, the definition, then we looked at a bit of the properties of the Laplace transform, then we wanted to look at Laplace transforms of general standard functions, which we wrote down here. So please feel free to leave a comment, drop a like, and don't forget to subscribe. Thank you.